At the center of our solar system sits a massive powerhouse. Over 1 million Earths could fit inside the sun's volume, and it constantly blasts out the light and heat required for life as we know it. When NASA sends robotic explorers into Earth orbit or out to nearby neighbors, they tap into that exact same energy source. The mechanics are straightforward. Spacecraft unfold large solar panels that convert incoming sunlight directly into electricity. That current powers the instruments and charges an onboard battery, which keeps the machine running even when its orbit takes it into temporary shadow. As long as we keep our spacecraft relatively close to home, the sun remains a reliable, infinite engine for scientific discovery. But that reliability drops off fast. As spacecraft travel farther out into the vastness of the solar system, that brilliant light dissipates, making solar panels an incredibly inefficient choice. Even on a relatively close planet like Mars, the environment can suddenly turn against a mission. A thick global dust storm can blot out the sky for weeks, starving a rover of the light it needs to survive. Then there is the danger of severe darkness. A Martian night plunges temperatures to -184 degrees Fahrenheit for 14 straight days. Or consider the Shackleton crater at the lunar South Pole, a place where the interior is always in shadow. To send probes out to the gas giants, fly them through the main asteroid belt, or study the icy, remote edges of our solar system, solar panels are completely incapable of doing the job. To explore the most extreme environments in space, we had to invent a way to bring our own power into the dark. The solution NASA developed is called a Radioisotope Thermoelectric Generator, or RTG. It's a lightweight, compact system designed for the deep freeze of space. An RTG harnesses the radioactive decay of plutonium dioxide, generating steady heat. This heat converts directly into electricity, powering the spacecraft's computers and instruments. Additionally, residual warmth bleeding off the RTG routes through the spacecraft, preventing fragile internal components from freezing in deep space. Because the power comes entirely from within, an RTG operates continuously. It ignores thick clouds, heavy dust, and the immense distance from the sun. This single piece of technology turns fragile, sunlight-dependent machines into rugged, self-sustaining explorers. RTGs gave us our first long-term foothold on the surface of Mars. The Viking 1 and 2 landers used them to easily survive those freezing, sunless Martian nights. Modern missions rely on them too. The Curiosity rover uses a multi-mission RTG to continuously study the Martian surface, entirely unaffected by local weather or seasonal changes. Beyond Mars, RTGs provided the endurance needed to push into the outer solar system. Pioneer 10 and 11 relied on nuclear power to safely traverse the main asteroid belt. That endurance allowed humanity to reach the gas giant Jupiter, transmitting the very first close-up science data of its magnetic fields and massive storms back to Earth. By deploying these generators, NASA broke through the solar barrier, establishing a scientific presence in environments where machines previously could not survive. This deep space power enabled massive, complex orbiters. The Cassini spacecraft used RTGs to spend 13 years circling Saturn, mapping its dense rings and discovering geologically active moons. They also powered the ultimate deep space endurance test. The Voyager probes pushed completely past the giant planets, leaving the heliosphere and flying out into the deepest dark of interstellar space. And when New Horizons finally reached the Pluto system, its RTG provided the power to capture the only close-up images we have of the icy dwarf planet. Without nuclear power, the entire outer half of our solar system would still be a complete, unmapped mystery. Over the past 60 years, the U.S. has flown 31 missions equipped with radioisotope power. These spacecraft act as our remote eyes and ears across the most hostile regions in space. The engineering choice between a solar panel and a radioisotope generator dictates exactly where we can go, what we can see, and even the ultimate limits of human ambition. To truly understand the vast, cold, and dark universe, we had to engineer a way to carry our own fire into the void.